So the slides are visible.
Yes, sir, visible, sir.
Okay, okay. So today's topic is about 5G and beyond wireless communication challenges. So I think this is visible, the slides. So as I say, we will start with the intro about this optical wireless communications, and then I'll move on to the what is the components of a optical wireless communication system. Then FSO communications using this adaptive and MIMO M-array PPM schemes, whereby the advanced schemes of how to deploy this FSO so as to meet the different objective of the next generation communications. Then I'll say some of the observations what we found from our results, and then we will discuss on the challenges that are open challenges that needs attentions, and conclusion, future scope, and some references. Well, so when you say about this free space optical communications, so it has got many advantages, but I always feel that FSO is a complementary technology to the RF. So both the technology has their own merits and limitations. But here today I will highlight on the FSO and what best we can achieve using this FSO for the next generation communication. So when you say about the FSO, it's a basically advanced wireless optical technology, and it is capable of enabling high-speed data services, which is required for 5G and beyond, as well as for 6G wireless networks. So right now, some of the countries where already this 5G is rolled out. Now the next target is to launch the 6G by the year 2030. But right now, though we are in the mid span of the 5G deployments, but many countries are there where till now the 5G has not yet rolled. And in Indian context also, many of the Indian cities have already got the 5G, but the areas are there where 5G is not fully rolled out. There are some challenges are there. So how this FSO can be act as an enabling technology to sort out those problems, that is also one of the point to be discussed during this presentation. So if you see about the next generation, what people are planning for the 6G, so there the target is to achieve extremely high capacity, and it is expected to support a wide range of new applications like a massive machine to machine communications. However, the current frequency bands what are being allocated for the 5G or to be allocated in the near futures are not sufficient to address these requirements. Then the other thing is that the 6G scenario, it is expected that it should enable superior coverage by integrating the air, space, underwater, as well as the terrestrial networks. So here the idea is that how to converge the different platforms so that we can extract the maximum capacity as well as the bit rate. So this is the other requirements. And if you see the 5G and the 6G networks, they have the provision, the possibility for enhanced broadbands, passive access, and ultra reliable and low latency services. So how do we see this from the optical point of view? If you ask me, you can see that FSO has this optical communication has got spans in all the different areas. Just now what I mentioned, it has got the reach in extraterrestrial space, it has got the reach in the free space optical domains, it has got the optical fiber based communications, as well as it finds application in the underwater communications. So if you can converge all this platform onto a single platform, then it is possible that we can get all the benefits of the optical communications, as well as we can realize very extensive large number of massive machine to machine and other communication forms, whereby we can provide the adequate bandwidth as well as the bit rates. So that's where the your optical communication stands. So it is a scenario which can be easily integrated with all the different communication modes like the terrestrials, the the interterrestrials underwater, as well as the your air-based communications. So that's the unique feature of the optical communication. So if you see the other aspects, the requirement for a high-speed communication is spectral efficiency. And if you see the radio frequency spectrums, the spectral efficiency has got the limitations, as well as if you see the spectrum bandwidth, that is also limited for radio frequency scenario, RF scenarios. So there we can pitch this FSO as a lone FSO or as a hybrid FSO, whereby we can go with RF FSO or FSO terahertz RF combinations. So this can be this could be a solution for this constraint on the spectral efficiency and on the available spectrum for the RF scenarios. However, as I say, these are the plus points of your optical communications. But at the same time, when you consider a free space optical communications, it has also got a number of limitations. To name a few, these are sensitive to temperature variations, and also it is the transmitter and the receiver apertures, the telescopic apertures, which plays a major role, whose positions can be easily altered by any kind of mechanical strains. And once it happens, it leads to the pointing errors. So that will completely creates a outage probability for the FSO communications. Besides this mechanical strains and your building sway effects, the other influential effect on this FSO communication is your atmospheric turbulence, which mostly depends on the scintillation factors, which in turn depends on the refractive index variations, which is again a function of the temperature. So it is not possible to maintain a constant temperature. So it is obvious that the temperature, the atmosphere will undergo various changes over a given time. And as a consequence of that, your FSO links are going to suffer from your this atmospheric turbulence and other effects. And all these effects combinedly will lead to this your losses, the attenuations, as well as the pointing error, which will lead to a very poor bit error rate. And sometimes it so happens that the link will be not usable, or you can say link is not available. And this is the scenario where the BER falls below your FEC threshold. So whenever somebody want to design this FSO for the 5G or for the next generation communications, there are some points need to be considered. One is that the reachabilities, the dynamic adjustment of this range over which the signal can be easily trans-received. That is the first things. The second thing is that how do we address the pointing array problems, like people use a system called APT systems, whereby acquisition, tracking, and pointing are involved. But if you try to implement this APT system, it is very complex to deploy. So is there any way by which we can solve these problems related to the atmospheric effects, as well as leads to the this your pointing errors that need to be found out? That is again a very important area of research. And one more issues are now coming up because of this requirement of a massive device to device communications. The requirement is the security. So how do we ensure the security over the FSO? So these are some of the points which needs a detailed analysis, as well as a more research on these lines before we roll out this FSO technology for commercial applications. However, if you see the after the drawback, again I'll go back to the advantage of this optical wireless. If you see the advantage, there are many advantages are there which will mask these limitations. As a result of that, this is an alternate technology, or you can say it's a complementary technology to the RF to realize the need of the next generation communications. Like if you see the first advantage is about the it's having a license free spectrum. It offers a very large bandwidth and a very it supports a very high bit rates. So on a optical fiber scenario, if you consider, as I say, we can convert all this platform so as to exploit the maximum bandwidth on a single strand of optical fiber. We can exploit the bandwidth up to 20 terahertz. But till date, we have only used or exploit 4 terahertz. So we got enough scope in that aspect, and it doesn't require any licensing the optical wireless, and its formats are transparent, so you don't have to have a protocol issues when you transmit over optical wireless. And it has it can be installed very easily. It can be implemented as a point to point line of sight link, or you can also design this as a point to multi point as a diffuse link. This optical wireless or the free space optics can be used as a communication process for your spacecrafts, satellites, UAV to satellite to grounds, and so. So it can be used in any platform, maybe in the air, maybe in the underwater, maybe in the terrestrial domain, or maybe in the outer space. Besides that, this optical wireless also find application for the military applications. So here, since it has having a very potential low electromagnetic radiations, one can transmit the data securely using this optical wireless. But there's still some challenges are there for the security aspects, though it is a very low radiating signals, but still a chance is there to tap the signals. So we need to adapt some robust techniques, like some research groups are working on different encryption for this optical wireless, but that makes the system complex. So we are working here on a scheme called a chaos aided secure optical communication system, whereby instead of generating the encryption and then it decrypt that one receiver sites, we are trying to add a chaos signals to the transmitted informations before we transmit over the channels. So once this chaos are added, the chaos will now mask the signal to be transmitted. So the person who will tries to eavesdrop on these signals, they will only see the noise, because it is the chaos is basically it's having no information. It's a chaotic signals which is generated by using a semiconductor laser diodes, but you have to directly modulate that using your chaos signals. So once that you do and edit it to the desired signal, this chaos signal will mask the original signals, and as a result of that, the eavesdroppers will not get a scope to get on the informations. So this can be used as a most reliable and a secure transmission link without the need of the encryption. So that is possible. And this optical wireless can be used as a backup to the fiber-based networks for your service accelerations. It can be deployed very fast. The deployment of OWC system requires hardly few hours, maybe 4 to 5 hours. So it can be used as a communication link for your disaster recovery scenarios where your all networks are down. At that point, one can deploy a OWC system, and you can attain all the features like the ultra low latency, your very high data rates, high bandwidth, low bit error rates. The bit error rate, I'll show some results where you can see that the BER is coming around into -9 for a distance up to say 9.5 to 10 kilometers, which is a significant range for optical wireless scenario. Without using much of the complex systems. So we designed very simple systems whereby the target was to not to use many amplifiers and also not to make the system complex. So that's why we didn't use the encryption scheme. Rather, we thought of using a chaos aided system so that we can ensure the security, and as well as for the your what do you say the range part. So we have used this spatial multiplexing techniques So whereby instead of using a single system, CISO system kind of things, point to point, we have used a MIMO system. So that's how we are able to design a system which not only is cost effective but also is secure. And this OWC's other requirement is that when you design a OWC, you cannot say that I will design a system that is very costly or very complex. Then the ultimate objective of the system design will fail. So that need to be kept in mind. So if you see the this optical communication system and its classifications, you can see that it is based on the wavelengths or based on the transmission range. So you can define this as a free space optical communications, whereby the operating wavelength is 750 nanometer to 1600 nanometers. And one can also have a VLC communication, that is the visible light communications, whereby the range will be 390 to 750 nanometer. And one more form of communication is there, that's the ultraviolet communication, but it is not yet popular. The range is 200 to 280 nanometers. Similarly, when you say about the reachability or the range, so we can define OWC into this five categories, that is ultra short range, or you can say the millimeter communications, which is being used in the chip to chip communications. Then we can have this short range communication, which is being used in the wide your this body area networks and this wireless body area networks and wireless personal area network applications. It has also got application in your underwater communications. Similarly, we also got a medium range communications, which is used in your indoor IR and visible based communication systems, where we use the VLC or the IR signals. It is used for wireless LANs, vehicle to vehicle communications, vehicle to infrastructure communications, and so on. It is in the meter range. It can also be used in the underwater scenario. So whereby the range can be up to few hundreds of meters. So right now, people are working on 100 to 150-meter range, but many of the literature you can see up to 50 meters, 70 meter, and so. Besides that, we can also think about this long-range communications, whereby inter-building connections are there, for which you can use FSO, or you can use this as a terrestrial backhaul links. We have tried up to 9.5 kilometer. It is working very fine and show some results. And besides that, one can also design a ultra long range communication system, which is being used for satellite to satellite or for your space communications, where the range would be more than hundreds of kilometers. So that's how we can classify the optical wireless. So from this, one can have a clear idea that, so since this optical wireless can be used in all the different mode of communications, so if we can integrate all this mode of communications, it is visible that we can able to realize a very high bit rate optical wireless systems which can support up to multiple of tens of gigabits for for required services of your 6G or the next generation communications, where we need a very low latency, ultra low latency, and a very high bit rate transmission sense. So that features can be met by converging all these different kinds of optical wireless communications. So in optical wireless, when you say the basically the technology used is what here it is a light which is being used for propagating over the free space, and the source can be a LED or a laser source, but most of the your long range or ultra long range communications we go with a laser, and for your meter range communications like your wireless LANs and your this underwater or your say B2B, there also we generally use the your this laser source. So this technology, if you see, one can go with the point to point or can go with the diffuse link, and the bitrate, as I say, it can support the very high bit rates of to few tens of gigabits per seconds. And the reachability, if you see, it can reach from millimeter to your and thousands of kilometers. So you can see that it can be used for your optical interconnects like chip to chip communication to your inter-satellite communications, or say satellite to space or ground station to space communications. And if you see the transmission spectra here ranges from 200 nanometer to 1600 nanometer. So this is a typical optical wireless architecture. So you need to start with the transmitter units. You have to have a receiver units and then the optical wireless channels. So on the transmitter sides, you need to have a optical source. As I say, the source can be a laser or LED depending on for what range communication we are designing the system. We have to select a appropriate source. Then we need to have a modulators. This modulator, we are not going with the direct modulation systems. The reason is that if you use a direct modulation system, there is a greater chance that the laser may malfunctions after a very short period of time, short use of time. So to make the laser lifetime extended, or you can say to make the laser more reliable, it's the best option is to go with the external modulation scheme. And so we need to have external modulators. We need to have a information source, what information that you want to transmit over the channel. So you should have an information source. It may be audio, video, text, or the, or you can say the images, or maybe a multimedia traffic. So this info need to be uh, impressed upon the optical carrier. So the laser or the LED, whatever you select, the spectrum what you got, that will act as the carrier here. So that carrier need to be modulated according to with your information source. So that's why we have shown here the resource data is now being driven by electrical signal driver, then it is fed to a modulator. So the output of the modulator, we got the modulated signals. So there are different kinds of modulation schemes are there. So you can go with a very simple your on-off keying to advanced modulation schemes like the PPM, MPAM, QPSK, and your DQPSK, and so on. So and then you need to, based on your transmission range requirements, you may or may not have to use an optical amplifier, but it is always wise to minimize the number of optical amplifier, because if you increase the number of amplifiers, so that you will increase your reachability, but at the same time you will also increase the cost of the deployment and also the maintenance. Then you need to have the your telescopic apertures for transmit, which acts as a transmitting antenna. Then you have the optical wireless channels, where, as I say, the signal will suffer from many detrimental effects over the atmospheric channels, like the scattering, the turbulence, the absorption effects, as well as at the receiver sides. Thus, when you try to couple the signal to the receiver, it will suffer from this optical losses, the system related losses. And finally, you will have this receiver telescopes, that is the receiver aperture. So you need to properly select the telescopic aperture and the receiver aperture, that are transmitter and receiver apertures. And also we need to see the misalignments and the both side errors, the pointing errors, how to address those issues that need to be properly designed. Otherwise, it so happens that you design a link, then because of this pointing error, the receiver aperture is not receiving any signals. So there will be a completely blankouts, or you can say there is a outage in the transmission link. So those need to be addressed. Then at the receiver side, you need to post-process the signals besides the pre-processing. So once you receive the signals, you pass it over an optical filter, then you have your detectors. Now, once the signal is passed out of the detector, you got electrical signals. You need to use electrical filter or a filter, a bank of filters. Then you post-process these electrical signals so as to observe the received signals BER and a Q factor, and then you have to have a demodulator. If you have something, you can demodulate and have your signal back. So the challenges in optical wireless I already discussed just now, but again I put them in this slide form. So you can see that for terrestrial application, the limiting factors are different losses in the system parameters. When you say the losses may be arise due to a physical obstruction. Suppose one design a optical wireless link for the very high bitrate communications, but suddenly say it's the link design is a point-to-point link. And you know this, when you say optical wireless, we are referring that there is a free space, or you can say the air is present, but when you mount these telescopes, the transmitting antenna, receiving antenna, it has to mount on some structures. So in between this, there should be a line of sight or maybe diffused mode. Suppose say we are on the line of sight, and if a bird will fly over that line of sight points, then it will create a obstructions. or suppose a tree is there which is outgrown, so that will create obstructions. So that will create again a issue on the bit error rate as well as your reachability. So this physical obstruction is one of the major issues. So before deployment, the place need to be properly surveyed. The next is that the next solution is that people are now also working on this intelligent reflecting surfaces for your optical wireless, whereby to get rid of this physical obstruction related issues. So they want to place the IRS in such a way that even if single path is blocked, the receiver gets the signal from a alternate paths. So that is the solutions. So now similarly, one can also have a scintillation or the fading effect due to the small particles which are available on the atmospheres. There may be the atmospheric related absorptions and maybe the turbulence due to the atmospheric temperature variations, the scattering due to the rain, the fog, and your snow situations. So these are some of the losses that your optical signal will encounter while passing over the optical wireless channel. And similarly, the other losses are also there, like that's related to the system parameters mostly, like the link range, the beam divergence angle, the receiver aperture, the transmitter aperture diameters, and the selected bit rate. And the other problem with this optical wireless links are that many of the time you'll see the links are not stable. They are unreliable and unpredictable links. So these are in general some of the drawbacks. But then when you try to deploy such a system, we know that these are the problems are going to happen. So we need to take the necessary precautions by which we can mitigate the problems what I already outlined here. So, as I already said about the turbulence-induced distortions, so when the FSO signals are propagated over the atmosphere, they will also be affected by this turbulence-induced distortions. This turbulence can be classified as weak turbulence, moderate turbulence, and your strong turbulence, which again depends on your this skin-cluster index parameters. So the values ranges from say 10 to or minus 15 to 10 to minus 12. So 10 to minus 12 is the strong turbulence, 10 to minus 15 or by minus 17 are there. That's so categorized as the weak turbulence. So this turbulence one can model mathematically, and one can see that. So what is the worst possible scenario, and what actions can be taken so that this turbulence related effects can be mitigated. So that need to be worked out by means of mathematical model, and then it has to be implemented. So this turbulence also results in this beam wanders, the scintillations, the phase distortions, which in turn degrades the signal integrity, SNR, and the BER. So this requires a urgent attention so that we can, when you deploy the FSO, the link should be reliable. We cannot work on a link which is not stable, which is not reliable. Then nobody will use that kind of a link. So we need to design a link which should be stable. We should not fluctuate much. It should be reliable and it should be readily available to the end users. That's the requirements. They use the term the scintillation and this beam wonder. So mathematically, you can model this using your this rate of approximations. So here in this expressions, sigma square in is the scintillation index. You have the Cn square, the refractive index structure parameters, and your this O what I mentioned here, that is the optical wave number, and this P is the transmission distance, and psi is the operating wavelength. So which can be user dependent. That means, as I say, the entire band is available 200 to 1600 nanometers. Based on the applications, one has to select, and then one has to substitute that number to calculate this scintillation index, which in turn will decide your link is suffering from a weak turbulence, moderate turbulence, or from a strong turbulence. Similarly, you can also find out this beam wonder, so whereby you need to use the same distance, the refractive index parameters, and this DIA, what I mentioned, that is the initial beam diameters, which is going to characterize the turbulence strength. So this is what the beam wonder. And as I say that one of the other requirement of this Next one is a communication, the spectral efficiency and the capacity. So the spectral efficiency basically defines how closely we can pack the info such that we can improve the bits per second per hertz capacity. That is the, or in other words saying, how do you increase the throughput? That is the transmission rates. So this data throughput per unit bandwidth, which is expressed as bits per second per hertz, is defined as the spectral efficiency. So that's, we need to see how can we pack the info into a unit bandwidth, more info, so that we can have more information which we can transmit over a given bandwidth. That's what a requirement and what can be best achieved using your this free space link. Another thing is that this presence of this turbulence will lead to the defading effects, and that will reduce the effective signal to noise ratio, which will in turn affect the channel capacity. If you go with the channel capacity theorem, we know that C equal to B log to 1 plus SNR. So in this case, I try to present that in terms of this SNR in terms of this fading effects. So here I replace that SNR by means of this expression, that is R into RP0 by N0B to a minus sigma square Ln. So here C is the channel capacity, B is the channel bandwidth, RP0 is the received signal power, N0 is the noise power spectral density, sigma square Ln what you see, that is the scintillation correction factor. So this basically governs your signal to noise ratio. So you can see that turbulence have a direct impact on the signal to noise ratio, or you can say in other words, the turbulence will affect the information carrying capacity of the designed link. So if you are encounter a strong turbulence, then the channel capacity will definitely will fall as compared to the weak or the moderate turbulence scenario. So the key technological contributions in the domain of advanced optical communications that our group is currently working is this FSO-based vertical backhaul frameworks, or you can say the high altitude platforms, or this 5G and beyond communications. We're also working on this terrestrial hybrid RF FSO links designs for 5G and beyond 5G communications, including the flying network platforms. So we are working on different advanced modulation formats so as to mitigate the atmospheric impairments. Similarly, we are also working on this MIMO schemes, whereby we have tried with different arrangement of MIMO using advanced modulation formats like M-label, PPM, and so on, which helps us in minimizing the outage probability, which is a prominent case for a single input, single output systems. And also, once you implement this MPPM, it is not only improving the outage performance for your MIMO, but also for the CISO. So that's what the one good results, that's what we observed over the years. Here you can see that the attenuations under different weather conditions for the FSO systems. So we have included geometric loss. The geometric loss is being shown here by this inverted triangles, and the turbulence loss is shown by this green lines, the rain attenuation by the blue lines, and the scattering loss by this your, or you can say the red lines. So this all these losses together will affect your link range, or you can say the reachability of a designed system. So if we calculate that up to 4,000 meter range for FSO, the total loss is coming around 15 dB under a dry scenario, dry atmospheric weather scenario. And beyond 4,000 kilometers, the atmosphere increases very sharply. As a result of that, the visible the VER falls very sharply, or you can say the Q factor deteriorates very sharply, so that you will not able to maintain the your FECs, and then the link will be lost. So this is the initial works where we tried up to 4.5 kilometers, and now we are reached up to around 9.5 to 10 kilometers. Similarly, here also you can see the range is shown up to 10 kilometers. So this is for different weather conditions, like a clear weather conditions and a bad weather conditions. Under bad weather scenario, the total attenuation may goes up to few hundreds of dB per kilometers. So in this case, it has shown that around 120 to 130 dB per kilometers. But that again depends if it is a cloudy weather or if it is a snowy weather, that will further increase the losses. So this result shows about the you say the Q factor versus the link range for different bitrate systems, which are subjected to different kinds of turbulence, like weak turbulence, moderate turbulence, and a strong turbulence. Both for 1G and 10G we have evaluated, and the results are shown here. So under this turbulence impact, we have seen that the link range is getting affected. So it is around 1.82 kilometers if the bitrate is 10 Gbps, and it is around 1. Sorry, it is 1 Gbps. The length is around, the reachability is around 1.8 kilometer, and if the bitrate is around 10 Gbps, then the bitrate, the range is falling to 1.5 kilometers. So in this case, we have only saw that impact. We are not taken any precautions here how to mitigate this problem. So this is without taking the you say preventive mechanisms. This is a simple system whereby the OWC is exposed to all the worst possible scenario for different bit rates, and this is what we got. And similarly, we have further investigated the OWC or FSO links by varying the your this mm, link divergence, or you can say the source um, optical beam divergence, and we consider a attenuation of 25 dB per kilometer a fixed loss for a average atmospheric conditions or a fair weather condition, you can say. And so here we have shown the receipt power versus the link range. So you can see the receipt power is also falling very rapidly once the link range is increasing. So this is obvious. As I said already, that it is a turbulence that is going to affect the signal to noise ratio. So the receipt power will definitely will be affected. So your SNR is going to fall. So this is the case where without taking any precautions. Similarly, this also shows a case whereby when you say that the multi gigabits transmissions, so in this case, it is the Q factor versus the transmitted power. So you can see that for the 10 Gbps lines under strong turbulence, so it is falling just below the threshold, FEC threshold. And for the moderate and for the weak turbulence, the link at 10 Gbps is working very fine. So signal quality is increased with increasing transmitting power for both the data rate signals. However, the problem is that if you increase the power by too much, then there is a chance of this non-linearity effect. So there is a trade-off. So what is the maximum power that we can pump, and what is the achievable Q factor? So it will only work up to certain upper limit of the power, and once you cross the threshold, so one will observe that there is no more further improvements, rather the link is suffering and it is going towards a outage scenario. So these are the points again to be noted while varying the power requirement of such links. So here you can see this is the model what is going to be best suited for this next generation communications, whereby we thought of converging this a hybrid RF FSO link with the backhaul planes as well as with the core network, and we have proposed here the flying network platforms. This flying network platform may be a UAV or a drone, and we have this terrestrial towers already existing. That's why I say it's a combination of a RF FSO as well as the backhaul networks, which is at the mostly the fiber. So and we use this flying network platform. So this converging mechanism is enabling us to achieve multiples of tens of gigabits per second transmission, and the received SNR is very, what you say, impressive. The data rate is, as I say, tens of Gbps, and the probability of fade is also under control. The outage probability is very minimal. So this is what some of the major features that one can analyze to see how the link which is designed by converging different platforms like terrestrial, the backhaul, the flying network platforms, and your RF is going to work out. So this link gives us a idea that, well, so by combining this all existing technologies, we can easily able to exploit the high bit rates with a ultra low latency scenario. And here you can see this terrestrial hybrid RF FSO link for this 5G and beyond 5G what we decided for operating. So the link range can be up to um, around means for a best link is up to 6 kilometer, but the link can work up to your 18 to 20 kilometers with a received SNR of minus 40 dB. So if your detector is sensitivity is more than say minus 40 dB, then your system can going to work up to 20 kilometers. So if you see in the first part of this plot where I put this dotted lines, so where I say it's a fog and rain limited zones, this part, initial part, this small section, and then this bigger part is a cloud zone. So the rain and fog zone is around zero point 0.1 kilometer to 1 kilometers for RFFSO vertical links, and a cloud zone, which basically the attenuation due to the clouds, that will affect significantly from 1 to 6 kilometers, and the pointing and the scintillation effects can be observed throughout the link from point 1 to 20 kilometers. So these are some of the uh, things to be addressed when we are trying to converge the different platform to design a hybrid uh, optical link. So that all these problems will come. So as I say, if you're having a flying network platform which is vertically flying, so there the different ranges are there. Like the rain and fog impact is only observed up to 1 kilometer, from 100 meter to 1 kilometer. Similarly, if it is cloud, this effect is from 1 kilometer to 6 kilometers. And if you have this pointing and a scintillation effect, that can be observed throughout the vertical link. That is, say, as high as you fly, you'll observe the entire uh, implements over the link designs. So here it is the vertical link which is tried up to 20 kilometers. That's what we are discussing there. So, and here the same link we simulated again for the horizontal scenario. In the horizontal scenario, we could reach up to 5 kilometer here using this platform. And the rain, path loss, and oxygen absorption plays a major role for this for the RF links. And the link availability of 0.6 kilometer and 2.3 kilometers under the thick fog and heavy rain weather conditions. If it is thick fog, it is 0.6 kilometer. It is heavy rain. The link can be achieved up to 2.3 kilometers. So it is the fog that affects more compared to the rain here. And this RF link will be made available up to 3.4 kilometer and 1.6 kilometer for clear and heavy rain weather conditions. So here, if you see the outage probability with the diversity schemes, what we adopted here, and similarly, we have shown the outage probability with atmospheric turbulence and the pointing error effects. So we can see the turbulence, the divisions like strong turbulence, moderate, and weak turbulence. So we define the parameter based on which we can classify as a strong or a weak turbulence. So weak turbulence we are calling as 10 to minus 17, moderate as 10 to minus 15, and for the strong it is 10 to minus 13. And this is the outage probability what I've shown versus the average electrical SNR. So in this plot, and here if you see the first plot, there again it plays the outage probability versus the electrical SNR for a given diversity scheme. So this is the solutions what I was discussing. So many issues are there. So we use this MPPM scheme, M-label PPM schemes using this multi-input, multi-output scenarios so as to uh, mitigate the atmospheric related and the pointing error related problems. As I said, if you got a CISO links and if you even a small birds fly over the link, you will see that the link is unstable. The link will fluctuate. To sort out that problems, what we did is that so we have taken the optical signals, then we have uh, divided that using a power divider, the same power, and then we pump that using different optical wireless channels. So, transmitting a single channel, we use the n number of channels. So this is the spatial diversity what we have adopted here. And by going with these schemes, we observe that the performance of the link is improving significantly. So here you can see the using this adaptive and the MIMO MPPM, how the average BER and outage probability has improved for different kinds of CISO, CMO, and MIMO systems with a link range of 5 km, having the pointing error parameter as zeta equal to 1.04 to 2.55. And here we consider first the two level PPM, but this can be further increased to a large numbers depending on the system's capacity, how much time it takes to simulate. And we did this simulation using this Monte Carlo simulation for double editions, besides the numerical analysis. And then this is the other part, what I was telling. So once we implement that MIMO systems, we observe that it is possible that we can improve the, or you can say the performance of the link because of this pointing error or because of the turbulence effect. So then we again analyze the system, including a defined, say, pointing error, which is not fixed, but which is, say, kind of variables over a time. So we change the your this pointing error in microradians from 0.2 microradians to your this 2 microradians with a total step of 50. Here the response what we got from this CISO and optimized 8x8 FSO, but in this case we didn't use the MPPM. So rather it is a modified duo binary return to zero schemes, whereby we use the a single channel or we use the 8x8 FSO using MDRZ. And the results, you can see that the Q factor results for the CISO and for the 8x8 system. So the 8x8 system, one can observe that gives a stable Q factor, which is more than 6.2 for all the distances. So it ensures that this link, which is designed for a 10 gigabits per second transmissions, is perfectly stable. It is reliable, and this results what I showed. This is the one where we applied the chaos, and we have used here a triangular chaos based system. So you can say that the chaos what we design is a triangular chaos, which is used to directly modulate the semiconductor laser diode, and the output of that is being added to the MDRZ signals. And once we transmit that chaos added signals, the receiver side, we need to use a coherent scheme to demodulate, whereby we use the same chaos generated to subtract the signal what we added in the transmitter side. We remove that one, and then we process it, and we observe that the Q factor what we obtained from this 8x8, this chaos added FSO, is a very secure FSO, offering a very stable link, which is not only reliable but also provides the guaranteed BER of 10 to the power minus 9, or you can say of the Q factor of 6.2 for all distances. That minimum is 6.2. So except for one or two outliers. So we have seen that this is working very fine for all distance up to 9.5 kilometer. So this is the things what we are currently working on, how to make the link more secure without introducing the encryption scheme. So once you say we are trying to deploy encryption scheme, it's make the system more complex. And if the encryption key is, say, lost, or it say somehow passed on to the eavesdroppers, they can easily uh, find out the info. And the realization of the encrypted system is also quite complex, and it's a costly affair. So in our case, without going with the complexity, we are simply presented here a chaos-based system, which is very robust, reliable, as well as secure. So, so this is what are some of the features that is highly essential for the next generation communications. Some more portions are there, but I don't know how much time. I think 10 minutes is there. So if you see the next generation, which is mostly the 6G, which is to be rolled out around 2030, the requirement is that to provide a seamless connectivity experience, it is expected to operate significantly at higher frequency bands, moving into the terahertz range. 6G will predict, learn, and adapt. That means your this AI and machine learning will be highly utilized along the 6G networks. So whereby we'll integrate this AI into the every layer of the network protocol so that 6G can manage resources very effectively. And the six, as I said, for the current work where we are trying to convert the different communication platforms, but in the 6G, the requirement is that to convert one more additional layer that's about the integration of the human, the physical, and the digital world onto a seamless manner. Also, the other expectation from the 6G communication is the holographic communications and the brain to machine interface, which is possible because of this ultra low latency, which may be of the order of microseconds. So that may be possible to realize going with the 6G network. So, but the major challenges for 6G, though people are working right now on this, are following are the six major challenge. One is the new spectrum technologies. There is no standardization yet, which spectrum to be used for the 6G. This AI based air interface, that is again a major problem because this AI will take a lot of resource, and how to make it a lightweight interface. So that is the other requirement. And in the 6G, the network itself has to act as a sensor. So that is the other requirement out of a 6G deployment. And the connectivity should be very extreme connectivity. That means it should be always available. It's like a extremely reliable link. It should has to be. The security and trust has to be there. As I said, we are going to now integrate the human, physical, and the digital world onto a single seamless platform. So the security and trust is a major hurdle. So we need to ensure that this is maintained. And finally, the cognitive, the automated, and the specialized architecture need to be built. So this architecture maybe will be completely different from the existing 5G architectures. So for this 6G part, or for the 5G and the next beyond technology, whenever you say that you are trying to use this FSO or the optical wireless, so it has also got some major challenges like the channel loss, atmospheric attenuations, the rain, the fog, the system loss, the geometric and the misalignment factors all will determine the link's availability, the link's reliability, and the link stability. So these factors will also will affect the link range, the availability, and the outage. We need to also look into the beam divergence angle of the source and what is the mechanism by which we can create the pencil beams. Then we need to think about the receiver aperture diameter optimizations, the different unfavorable conditions, the signal quality, and your power. How do you optimize it? As I said, it is the atmospheric effect what are going to affect the SNR. Once the SNR degrades, that will automatically will downgrade your channel capacity. So we need to work out on the mechanisms by which we can mitigate this atmospheric related problems. And finally, the FSO system parameter optimization is also is highly essential for its deployment. So these are some of the references what I use while preparing this. So that much. So if you have any queries, I'll be happy to answer your query. Yeah, any queries? So I'll be happy to answer. So the simulation platform what we use mostly it is the MATLAB, and then we also use the OptiSystem 22.1 version. About the practical deployment cost of this FSO, we need to, as I say, the major cost will be about the source and the receiver sites and the processing part. So it will be around for a campus kind of scenario. If it is on a point-to-point link, the cost will be something around 15 to 20 lakhs. And so this FSOs are, as I say, from our results, we concluded that key up to a range of 10 kilometers, we can deploy this. So for a bigger campus, it is a good solutions. However, it can also be used in sync with the beacon so as to provide a connectivity in a small towns, many towns you can say, where the radius will be around 5 kilometers. So we can provide that, but the deployment cost will be for a urban area maybe ranges from say 20 to 60 lakhs, but for a campus environment will be around 15 to 20 lakhs. And name of some FSO 5G projects in India. This all are working in individualistic projects, so I cannot name it, but we have this 5G forum is there. So right now, this DOT is running a platform where you can log into there and you can see all the running 5G projects. But those are not mostly FSO based; those are all RA based. And about your 6G network possible in near future, yeah, it's possible. As I say, the planning date to roll up is 2030. So many of the European countries are working on this. Also, some part of US they're working on 6G deployment, and Asia also China is working on. In India, a few institutes are working on this 6G deployment. Some test bed work is going on. I don't want to name some of the institutes who are working. We are also planning to set up a 6G test bed. So that's what. I think you are mute.
Thank you, Prashant.
Thank you. So I hope I maintain the time. I didn't supersede
Yes,
your time limit.
that was essential.
Thank you.
Our next speaker is also from IIT Bhubaneswar. So we,
I'm not able to hear you. Your voice is a bit low.
am I audible now?
Ha ha ha. Right.
You watch.
Yeah, it's audible now. Yeah.
Okay. So our next speaker is also from IIT Bhubaneswar.
Oh, great. Oh,
It's
Soumya
Dr. Soumya Prakash
Das.
Das. Yeah.
Okay, fine then. So, thank you. Thank you for inviting. So, let me thank the organizers once again for this invitation. I hope I share some
Pleasure is ours,
ideas.
and we believe the participants are benefited with this knowledge.
Thank you. Thank
Thank
you,
you.
Professor Ravi. Thank you then. Thank you to all
Thank you.
participants also. Thank you. So, now I will log out.
Yes, please.
Thank you.
Next, next number. Yeah, next